Swayam Prabha. Digital India. Educated India.
Good morning everybody. Today we are going to discuss a very important aspect of vacuum science and technology, that is the measurement of vacuum. You all know that unless you measure something accurately, your product is of no use, because predicting the performance of a product is possible only if you have some quality control, if you make some tests on it or measurements on it. Okay. Of course, physics is a study of perfect precise measurements, and every technology has got a background physics. So, when it comes to vacuum technology, we have to measure vacuum, because pumps are there, systems are there, applications are there, troubleshooting, everything fine. But what is it? How much level of vacuum? Is it correct? Is it to be controlled or is it to be monitored? What type of precautions we have to take? What we are measuring? What is the resolution? What is the accuracy? Are we what you call adding some perfect correct value, or we are just saying it's okay, it's a good vacuum, bad vacuum, it's a qualitatively talking, it has no meaning. Okay. So, measurement is most important phase of any technology, and even for vacuum technology. First phase is production, then measurement, then only you can start designing and applying and troubleshooting or marketing, etc. Anyway, this is general introduction about importance of measurement of vacuum. What is measurement of vacuum? It is nothing but measurement of pressure only. There is nothing like vacuum measurement, because vacuum is a state. Okay. Vacuum is not a quantity. Quantity is pressure. That is why what we are going to measure is pressure, but popularly we say measurement of vacuum. That should be kept in mind. Here we are going to cover the concepts like introduction to primary and secondary gauges. Within that, primary gauges we will see in this class, and some useful secondary gauges we shall see in the coming classes. Within the primary gauges, we are going to discuss U-tube manometers and McLeod gauge. There are also some other secondary primary gauges. They are not secondary gauges, they are also primary gauges, little different, but they are also quite good gauges. That also we will be covering under primary in the next class. Okay. What is primary? What is secondary? Primary means you are trying to respond to the pressure of that ambient directly based on certain fundamental principles which cannot be questioned. F is equal to ma, we are not going to question. Okay. P2 minus P1 into A, force, we are not going to question. Okay. P1 V1, P2 V2, we are not going to ask any question to anybody. So, fundamentals if you are using, which are well tested, then the gauges which are working on fundamental principles, they can be called primary gauges. Or in the simple language, if they respond directly to the pressure or force or directly, then they are called primary gauges. Examples are manometers, little higher level McLeod gauge, then we have capacitance gauge, spinning rotor gauge. These are all fundamentals related primary gauges. In the sense they are very accurate, they are little time and space independent, whether you measure here or whether you measure in some other country with that gauge. It will not vary much. Of course, you have to have international standards for everything, and every country standard has to be cross checked. All that is there, even for a meter length also, for a degree centigrade, for 1 gram. Though we say it is simple, but in practice, in physical standards, it has to be monitored under international scale. Same thing is true for vacuum measurement. Okay, secondary gauges are, they do not respond directly to the pressure. They respond to some physical property variation due to pressure change. If pressure is changing, that property is changing, we are measuring that property and correlating it with pressure changes. That means, we are measuring vacuum not in the direct sense using some fundamental principles, but using some related parameters which are user friendly, may not be that accurate, they are secondary gauges. We need to calibrate them using primary gauges now and then, and recalibrate the moment you get doubt that something is getting spoiled, it is not measuring, etc. Quite often it happens in the lab. So, we will have to do all that for secondary gauges, whether primary gauges should be kept as standards in the lab scale or institute scale or country scale or in the world standards. There are levels of standards. So, primary gauges are to be given a lot of respect and they should be handled very carefully. We will discuss primary gauges today, later we will go for secondary gauges. Secondary gauges are more friendly in the sense you can convert them into digital display. You can use it on a very fast mode, where the primary gauges are very slow, and discontinuous measurements, you have to do lot of precautions and make one measurement for a long time. But secondary gauges are dynamic, but they may not be accurate and they need little bit of calibration every now and then. What are those parameters or properties of a gas which depend on pressure, like a thermal conductivity variation, which is exploited in Pirani gauge, which is very popular in our country, as well as thermocouple gauge. Once upon a time it was very popular, even now it is being used to get a rough thing, but there are some errors associated with that. In fact, for every gauge there are errors. Okay, we will see calibration procedures and limitations. And if you go for very high level of vacuum, you depend on some other property of gas, which is ionization aspect of that. Ionization current variation, its variation with pressure is picked up and we get a value of pressure. It can be digitized also. So, whether we use thermal conductivity variation with pressure or ionization current variation with pressure, these are secondary gauges. Primary gauges are directly force related or some fundamentals related. Okay. Those things we will see now. Sometimes you will find very peculiar things in some refrigeration industry or somewhere. You will find lots of dial gauges where you need to evacuate also refrigeration compressors, etc. When you are refilling, first you have to remove it with a vacuum pump and you have to evacuate. This is a very standard procedure is there. This is one of the mega applications in a large scale of a rough rotary pump. Okay. So, when they do that, normally the gauges they are connecting to the system to measure the high pressure, because the compressors are at high pressure. But during this purging or refilling, we are evacuating the whole thing. That time we also need a gauge which measures vacuum. There we will see when no pressure is there, they will call it as 0, but actually it is not 0 pressure. When you vent the whole freon gas or whatever it is totally in equilibrium with atmosphere, we simply say it is 0. No, it is 0 with reference to atmospheric pressure. if you take reference as the atmospheric pressure. But if you take reference as the 0 pressure, 0 is not possible, that is a different thing, but 10 power minus 11 minus 12 type of thing. Then we are measuring absolute pressure. Absolute pressure can never be negative, whereas the relative gauge pressure that we sometimes measure using Bourdon gauge in some industrial atmosphere, sometimes we find negative scale. Negative pressure cannot be negative. Okay. Only conceptually you can say vacuum is negative. The engineers working in that refrigeration industry they are more bothered about their lifeline refrigeration, high pressure, filling, freon. They are not worried about few minutes of evacuating, etc. So, for them it is a small aspect of it. They will say minus, and they get mentally, they will be convinced that now I am removing the gas. So, pressure is going negative. This is why I am saying is, I found this problem. I have organized more than 35 courses for industries, with industries, and for various R&D organizations, etc. At times I am facing this type of situation, but finally we could convince each other and try to explain them. But it is okay, if it is not of importance to you, whether you call negative, it does not matter. But when it comes to science, there is no negative pressure. Okay. It is always positive. It is with reference to perfect vacuum, which we call it as 0 pressure. Okay. So, positive or negative, there are different scales, and even if you see all those scales, again you get confused. So, just read this statement and get a feel of it. So, absolute measurement. This happens in temperature also, 0 degree centigrade, and then I will say minus 10, minus 20, minus 30, like that. So, but when you go to the absolute scale Kelvin, 0 is 0. There cannot be minus 0 Kelvin, minus 2 Kelvin, minus 3 Kelvin. The concept of temperature itself will start with 0 Kelvin. That is called absolute temperature. This we are used to it in thermodynamics, etc., because we use it to make several calculations in isenthalpic, isentropic process and all. That T has to be there in SI systems, etc. Otherwise, centigrade is a very useful thing, very friendly thing, but still we will have to use in Kelvin, etc. Whereas in vacuum, those industries which are working in electronics, 10 power minus 7 or minus 8 or they are fully aware we are measuring absolute pressure. But some process gases where now and then they make negative things, we should be very careful, but there is no negative. Okay. Having said that, having understood the difference between primary and secondary gauges, now is the time for us to go ahead with various technical aspects of pressure measurement in vacuum systems. Best measurement, best way of measuring the vacuum is U-tube. Why? U-tube measures in a fundamental way. If there is a pressure difference in a U-tube having mercury, automatically higher pressure pushes down, otherwise Pascal will be unhappy, and automatically level will be different. It is nature's law. Okay, higher pressure side it will be pushed. And why U is there? Because you need to fill the mercury, that is acting like an isolation between two pressures. And sometimes when it is rising, etc., some people call it as a piston type of thing. Okay. But when you do all this, depending on the pressure difference, there will be one P high and P low. U is because, U shape is because when you fill the liquid, you can keep the liquid in that shape only if both the limbs are taken up and then connected, one to the reference and other to the system to be measured, whose vacuum is to be measured. Okay. So, U-tube is a compulsion. You cannot take a straight pipe, then mercury will fall down, unless you keep a trough and then put it invert and all those things like Torricelli did, that is a different thing. But otherwise, U-tube is very famous meter. It is also used in routine laboratories for measuring pressure difference. Pressure drop is a very important aspect in mechanical engineering, pressure drop. Okay. That multiplied by volumetric flow rate, okay, will give you pumping power, etc. So, the pressure drops of very small quantities are also measured by U-tube. In vacuum also sometimes people use this for measuring with the pressure differences within the vacuum range also. But U-tube manometer is extremely useful and extremely accurate with the fundamental principles that P2 minus P1 is equal to rho density of the fluid that you are using. Most of the time we use mercury for obvious reason, because levels will be little, quantities will be less, which are manageable with your hands and eyes. Otherwise, if you use water and all, you have 10 meters and the relative densities are different, and multiplied with a g and gravity and multiplied by the level difference, not the level difference. If you take one side as 0, then it can be called as level height or something, that is pressure head, people say like that. This delta H is also measured in millimeters of mercury. Millimeter of mercury is also called tar. So, in a way the levels are measured in the same style as the quantity to be measured in tar. So, tar pressure H, this is of course known to mechanical engineers, pressure head type thing H. These are all in the similar language, they are related to each other. Okay. So, U shape is coming because you have to maintain the liquid without overflowing, and it is basically a liquid balance. It is a liquid balance, depending on the forces it will take up and down like that, whichever is positive pressure, higher pressure. So, the accuracy of measurement of this height delta H, it is this which is going to play finally the what you call limitation or accuracy, whatever it is, when you use these gauges for measuring vacuum. Why? What happens when you are connecting one side to the vacuum, other side to the atmosphere? As you start evacuating, the atmosphere will push it down. You can also have another version where one side is connected to a limb, which is a closed thing, and it is perfectly evacuated and sealed. Then perfect vacuum side is always higher, and if this is also perfect vacuum, then it will be same, otherwise it will go this way. So, if you look at the figure, there are two configurations of U-tube manometer. When the reference arm is connected to the atmosphere, or reference arm is connected to a high vacuum in a sealed pipe. Here it need not be sealed because it is exposed to atmosphere, infinite volume, no problem. Here we are exposing it to high vacuum. So, these vacuum system to be measured, it is much poorer compared to this, so that you will have meaningful experiments. Here also vacuum system to be measured is connected to the left, but right is always higher than left. Here right is much lower compared to the left. Both these configurations are quite popular when you are using this U-tube for measurement of vacuum below the atmosphere, that is from 1000 millibar, very strictly speaking 1013, and I do not bother about all this in engineering, 1000 millibar. Okay, 1 bar 1000 millibar, very comfortable. Units you have to be very careful. After all, we are doing pressure measurement. If you make a mistake, you are gone. Your application will not be there. If you try to make 10 power minus 7 as minus 5 and try to deposit a thin film and use it for IR detector or use it for semiconducting device applications, it will not be working properly, because it is what you call impure, because minus 5 tar is much less cleaner compared to minus 7, and you have thought it is minus 7 because your gauge is not proper. So, you should be very careful in measuring these things. So, why only 100 millibar, you can go up to 1 millibar, 10 power minus 1, minus 2. No. Why? Logic is very simple. One side, let us say 1000, other side 1, other side 10, other side 100, other side 1000. When it is both sides 1000 millibar, it is 0. Then as you start evacuating, it will go up. With our naked eye, how much we can pick up the change in this height change, that meniscus both sides, maximum 1 millimeter, because most of the graduations are also millimeters. Our eye cannot see below 0.1 millimeter, etc. So, millimeter of mercury is called tar, little bit different compared to millibar, because both are in a very rough scale. We will say millibar or tar are more or less same, but we normally officially we cannot tell 1000 millibar 760 tar, or I would say 1 millibar 3/4 tar. That way you can say that. Okay. So, once it crosses 10 millibar, the difference is already 750, because one side 760, other side is 50, 750. So, you will have to be careful. If it goes to 1, 759, if it goes to 0.1, 759.9, but you cannot measure 759.01, which is just a normal vacuum with respect to rotary pump. 759.99, we cannot do this. And even if you keep with very accurate instruments or microscope or something, telescope, you cannot do that, because if there is a fluctuation or something, vibration, it may change. So, even if actually the levels are changing, but you are unable to, measuring sensitivity is not there, you are unable to measure. Okay. That is why you cannot use this U-tube manometer below 10 millibar. Even sometimes people say 50 60 millibar. Below that we start getting errors, 5%, 10%. So, with this idea of U-tube manometer limitation, then what to do? We need an accurate measurement for 10 power minus 1, minus 2, minus 3, minus 5, minus 7, minus 10. Otherwise, electronics, computer science, metallurgy, nuclear, space, molecular distillation, pharma, all these people are saying we want to measure accurately. Okay, Pirani has given a gauge, secondary gauge, which is good enough for getting an order of vacuum, but we need to measure accurately for monitoring properly. Otherwise, our products may not be quality products. So, we need another standard. But it went on for some time in the history till another intelligent physicist came, and what he did is very simple, that is called McLeod gauge. McLeod gauge is a very, very fundamental gauge. In roughly 1856 or something, it is started from McLeod, and even today that is the primary gauge, that is the gauge which is to be used to calibrate other gauges in national laboratories. Every country has got a national physical laboratory where the standards are maintained, vacuum standards. We have in Delhi National Physical Laboratory a big division with a lot of sophisticated equipment, etc., and perfect cleanly systems and all to make accurate measurements. So, most of the companies will have to take their gauges and randomly they have to give a sample and may ask them to measure with their primary standards, which they maintain with a lot of care, and give you a certificate, and afterwards you can sell with that. So, this way this McLeod gauge has increased the sensitivity of primary measurement based on some fundamental principles. P2 minus P1 force concepts, Pascal ideas, it is fine. But what else? He has combined the Boyle's law. By that time Boyle has discovered his law. If you maintain a constant temperature, P1 V1 is equal to P2 V2. So, this U-tube is converted into another style of U-tube. Even now it looks like a U-tube only, you will see, but it has got some extra attachments. Left side there is a big bulb collecting area and there is a small capillary. I am covering the construction. which is a closed capillary. Right side there is another pipe with a parallel combination of a capillary pipe. The capillaries of these two capillaries are identical, so that meniscus effects are similar, so that you will not get any error in the measurement, particularly delta H measurement, because you cannot take this, meniscus shape will be different. But you need a big tube to collect this vacuum, to communicate this vacuum for measurement, and this gray color is mercury. And with some arrangement here in the bottom, where you can connect a reservoir with mercury and you can raise that mercury up and down. This is a very simple thing, you can understand. It is available in YouTube. After all, this is also YouTube, and YouTube is so popular, so you can easily get lot of animations and all. I am not showing animation because I want you to understand fundamentals. Animation is comfortable, but if you do not understand fundamental, then it is not good. Okay. A reservoir of mercury with a means to is attached to raise or lower the mercury level. If you lower the mercury here, parallelly this will also come. We need not say, because nature says that. Okay. This is a typical physics principle. Okay. Now, when all of it is down here below this point called X, diversion point, that is where the system whose vacuum we are measuring is communicated through this pipe, which is quite big, through this into a big bulb which is made out of a glass with a small capillary extension. So, if the volume of this bulb is capital V, you can neglect this extra volume of the capillary whenever these are additive, but if it is a ratio you cannot neglect. Okay. And by raising up and down you can communicate this system vacuum to be measured here. At the time of isolation, at that instant of time, whatever is the vacuum, that is what we are measuring. Then we need to do some exercise to make measurements, that we will see now, some manipulations. By that time, if vacuum level changes, we are not responsible for it. We are measuring that instant of time when this got isolated. So, at that time when it is getting isolated in the system, if you connect another secondary gauge, whatever is the reading of the secondary gauge, you take and keep it. That reading will be calibrated against this vacuum that we are going to compute after collecting an area. So, what McLeod has done is, instead of continuously measuring like a YouTube manometer, he collected a sample of gas through a big pipe, and initially by lowering this mercury down, that mechanism, several varieties of mechanisms are there. Okay. You can have a pump, or you can have another YouTube connected to up and down measurements. There are varieties of things depending on the convenience you want. Okay. You can connect a diaphragm pump with a reservoir of mercury and make it up and down also with change of, with just by rotating. So, when you lower the mercury, a sample of gas is collected. It becomes a sample when you are raising it. If you cross the X, then it is isolated. It is like a rotary pump, collect the gas, isolate it, compress it. Now, that production concept we are using it again here, but all isothermal. Okay, because we are slowly doing, mass of it is so high compared to these grams. So, the heat of compression is not at all there. Okay. So, when you are trying to isolate the particular amount of volume, which we mostly consider it as a V, because V is the biggest, that's most of the volume is V now, or we can even calibrate how much is this much by filling the water and again pouring it out. So, you can know this free volume, that is my initial volume. What is the initial pressure? The system pressure, which we want to calculate. Now, you try to raise it further. You have already collected, you have isolated because the mercury level has crossed X. Now, it is going up and up and up. After that, the entire air that is trapped in this bulb above X level is going to be compressed into a fine capillary whose volume is almost negligible compared to this, and this mercury is acting like a piston in a closed capillary. Under that situation, the final volume here for the same number of moles of gas that are being collected at the time of isolation, N is same. So, T is same, R is same, P1 V1 is P2 V2. Initial volume is V, initial pressure is unknown pressure, final pressure is a measurable pressure because it is a compressed thing. When you collect even 10 power minus 1 minus 2 which cannot be measured by a U-tube meter, now we can measure because that 10 power minus 1 is compressed 1000 times to almost 1/10 tar. 10 tar is easily measured by U-tube principle. Wherever there is a parallel paths in a U-tube connection and if it is identical shapes, the level difference will automatically be there. That fellow will take care of that. So, the level differences can be calibrated, but with some suitable mass, I am not going into the details of it. If you make this alignment every time for every measurement, now it is 10 millibar, later 100 millibar. For every measurement, start collecting, isolate it, raise the mercury that is in your control till the top level of this parallel path of this collecting point to the top point of this closed capillary. That correction if you make, you can work out the mathematics if you want, it is worked out everywhere. I am not going into that, I want you to understand the principle because of limited time. Then you will see the P1 V1 P2 V2 when you use, you can get the vacuum. Actually, I am explaining it along with construction, but actually I have already explained the principle. Though it is construction slide, it is already working principle slide. You please read it at your leisure. So, same figure I am putting it here for your convenience. So, reservoir is made to make the level down, collect the thing and make it up. Just whatever I have told, initial value is P1, V1. What is the final pressure? Whatever is that unknown pressure plus the height difference between two columns, this capillary and this capillary, because this is same vacuum as this, but it can take care of capillary effects, meniscus effects. So, final pressure is P plus H in the consistent units, in the head units. Final volume is cross sectional area of this capillary multiplied by the height of this capillary, the remaining height of this capillary, okay, which is called H. So, if you do that, the actual pressure is to be measured is 10 power minus 1 minus 2 type thing, whereas the level differences are few millimeters. So, 10 power minus 2 is hardly negligible compared to 100 millibar, which is the final pressure, because H is quite high, 20, 30 millimeters height of change may be there. So, actual pressure after compression may be quite high, 30 millibar, and this was 0.01. So, P to be measured is negligible when it is added mathematically. So, this becomes H square. Left side is P. Very accurately, if you want variables, separables, you do, that is up to you. But otherwise, a first order approximation, engineers always want 0.1% error enough. But if you go to science, you have to take care of every small thing. Okay. So, then it becomes a simple equation. So, every time what you do manipulations, first mercury level down, collect the system pressure at that instant of time, keep a note of the secondary gauge which is connected to the same chamber at that instant of time when it is isolated, and take that as unknown, as to be calibrated value, and at that time whatever is the value of that vacuum level, if that was P, that was now getting compressed to another higher pressure which is called P plus H with reference to this vacuum, which is whether it is 0.01 or 0.001, even though it is changing, the level will not change much because higher pressure is this side. So, P plus H is going to be more or less same, and this P is the signature of the original thing which was at 10 power minus 2 tar, same number of moles are being compressed. So, by knowing the compression ratio which is V1 by V2, P1 by P2 can be calculated. Okay. The P unknown, that is P, which is initial pressure, and initial volume V, because that is the major volume. Final volume is this, which is very small, P2 will be high. So, P2 by P1, P2 is known because P2 is a measurable fellow, because a higher pressure easily measurable. V1, V2s are measurable, these are volumes only. So, P can be measured, and with approximations and adjustments, this will come out to be H square A by V. This is how you make the measurement. I will not go into detail because of lack of time, I think I am already running short of time, but this is explained very well. This is 200 years, 150 years back they have done it. You can easily understand now. Okay, it is a school level thing, but many people get confused. That's why I am trying to explain very elementary language. Okay. So, by adjusting the volume of the bulb quite big and by properly making very high quality capillaries, etc., they can be, this sort of instrument can be used right down to 10 power minus 5 torr using Boyle's law and the pressure difference concept. But this is a discontinuous measurement, that is the thing. But anyway, okay, that one pressure, various fixed points you can measure and plot it as x-axis. Y-axis is the equivalent value whatever display of a secondary gauge of a company, that will be there, and you say this is the correct pressure. If that is not there, add some calibration constant and make it coincide. That's how you do the calibration. So, with this type of ideas, this primary gauge, today we are in a position to measure very accurately vacuum in process applications. In 100-200 millibar, U-tube is good enough. So, we have seen U-tube and primary McLeod gauge as primary standards. There are capacitance gauges which also are primary in the sense they measure deflection, mechanical deflection and rotation of a sphere, etc., viscous drag, those concepts. And we will see thermal conductivity variation and ionization variation for secondary gauges. So, all these things we will cover it in the coming classes. So, with this, today we have completed classification of pressure gauges and primary gauges which can be used as a primary standards to calibrate the secondary gauges, which is a very important aspect of measurement in vacuum technology. Thank you very much.